Hello, good day. How are you? Let me continue the discussion of chapter 14 problems. Chapter 14 is all about statics and elasticity. When we speak of statics, we are talking here of equilibrium conditions. We are talking of objects acted on by several forces, and this object being acted on by several forces remain at rest. Okay? So you have problems there. The first, I think that is the first set of problems for assignment number 6. I was providing you all the problems, and those problems are taken from our textbook. Okay? And these problems are well selected in such a way the concepts as discussed in the book will be applied, and the principles governing the concepts will be in operation of these problems. They operate. Okay? Now, problem number 1. I'm holding here the book. Okay? I have a video on problem number 1. Okay? Now, you have to listen to my audio because some writings I made on the board could not be seen. Okay? When I looked at the video, my video on problem number 1, there were writings on the board not seen in the video, and therefore my audio will guide you. Okay, the audio will guide you. While you cannot see the physical quantities involved there, you can hear what are those physical quantities, because while writing those physical quantities on the board, I stated the physical quantities I wrote on the board. So you review the video again and again. Okay? As you observe in that discussion, it is just a continuation of our previous problems in chapter 5. So, we jumped immediately to chapter 14 because the principles applied in chapter 14 are the same principles we discussed in previous chapters, and one of these chapters where most of the principles are being used in chapter 14 is chapter 5. Okay? Okay. Now, let me proceed to the next problem. By the way, when you solve the problem, as I explained that, be sure, my dear students, you do it legibly, huh? Be sure you make your solutions readable, and the solutions are done in details, step by step. Okay? Okay. Now, let us proceed to problem number 2. Problem number 2 now incorporates the concept of torque. Problem number 2. We cannot solve problem number 2 without understanding torque. Torque. T-O-R-Q-U-E. Torque. And this physical quantity is the one responsible in rotating any object around you. The wheels of the vehicles, the motorcycles, the bicycles, they rotate because of torques. When you buy an automobile, a car or a vehicle, there is always that physical quantity we call torque. The torque of the vehicle is very important. The greater the torque, the stronger the vehicle. Okay? Another example of torque is when you open the door. When you open the door of your house, of where you are located in a building, or where there is a door, when you open that, you apply a force, but that force is useless without a torque. And torque refers to the force applied and the distance from the axis of rotation to where the force is applied. And that distance from the axis of rotation, we call that the moment arm. Or other books call that the lever. Okay? So, using the door, when you open the door, you hold the doorknob. Let's say your door has a doorknob. You hold the doorknob, you open, you apply a force. That door opens because of the torque, not because of the force. Because if it were the force responsible in opening the door, then if you are going to transfer the doorknob nearer the axis of rotation, where is that axis of rotation of the door? The axis of rotation is right at the hinges. In Dumaguete, the vernacular of hinges gitawag na og bisagra. Bisagra. Hinges. So the door rotates at the hinges. The hinges serve as the axis of rotation. I'm referring to the rotating door, not the sliding door, Oh, not the sliding door. The rotating door. So hinges. You put the doorknob near the hinges. Which is harder for you to open the door? When the doorknob nearer the hinges or farther from the hinges? Which is harder? Suppose your doorknob is transferred nearer, closer to the hinges. Experiment lang yun. When you open the door, you need stronger force. It's harder for you to open the door. And more harder when you put the doorknob nearer and nearer, closer and closer to the hinges, to the bisagra. And the hardest, and which is impossible to open the door, is when the doorknob is right at the hinges. And so, you cannot open. There is a force, but there is no torque because the torque there is zero. Because the torque is not only about force, it is also about the moment arm. That moment arm, we define that in physics as the perpendicular distance from the axis of rotation to the line of action of the force. That's the moment arm. It is the perpendicular distance from the axis of rotation from the hinges to where the force you apply. And you apply the force right at the door knob to open the door or close the door. Okay? So, torque is not about a force only. It is also about the moment arm. And I'm going to put down this book so that I can use my arms in writing equations on the board. Okay? Okay. Here, my dear students, torque, 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 okay? T-O-R-Q-U-E, torque, is equal to the moment arm, moment arm times the force applied or the applied force. The force here refers to that force where you are going to rotate the body with the help of the moment arm. The moment arm and the force, multiply them, you have the torque. Torque. Okay? Okay. So, in symbols, you have the Greek letter tau. Tau is equal to R, the moment arm, okay, times the force. Here, by the way, torque is a vector quantity. So this is, there's an arrow, this one is a vector, this one is a vector, this is the radial distance, or let us just say moment arm times the force, which is a vector. You have here actually a cross product. And when you have a cross product, if we get the magnitude, so magnitude here, we get the magnitude of the cross product, the magnitude there, you will have here torque on the magnitude is R F sine theta, where theta, angle theta, is the angle between the moment arm and the force. Okay? So this is the formula. Now, theta, okay, will give a value to the torque either bigger or smaller value. The smallest value of torque is when the angle is zero. When the angle is zero, sine theta, where theta is zero, the sine of 0 degree equals 0. And when sine theta, sine 0 equals 0, the result here, this is 0, 0 because sine angle 0, sine of 0 is 0, 0 times F times R equals 0. The torque is 0. That's the smallest. When theta is 0, torque is 0. And the maximum value of the torque is when theta, the angle theta is 90 degrees. Sine of 90 degrees is equal to, what is the answer? I will answer my question. 1. And that happens when the moment arm is perpendicular to the line of action of the force. Remember that theta is the angle between the moment arm and the force. If you have the moment arm vertical to the line of action of the force, vertical means it has an angle of 90 degrees, then sine 90 is 1, you have a maximum torque. Okay? Okay. From 0 to 90, there is a variation. From 0 to 180, of course, you are going to use their trigonometric functions now, and you will find that when the angle is 180 degrees, torque is 0. When the angle is 360 degrees, torque is 0. When the angle is 270, and sine of 270 is not 0. Right? It's 1. And because it is along the negative y-axis, you have a negative 1 in terms of direction. Okay? Okay? Okay. Now, so this is the formula. So you have here, if where theta equals angle, the angle between R and F. Between R and F. For instance, let us have a top view. Top view of the door. Top view, looking at the top. So, looking at the top, okay, you have here, what you see, this is the thickness of the door. Okay, this is the thickness of the door. Top view, top view. And somewhere here is the doorknob. This is the location of the doorknob. Top view, looking from the top. And you have here the hinges. Okay, let us say there are two ends here. This is end A, and this one is end B. Where end B is the location of the hinges. Bisagra. Top view, top view. When you go into your house, you are not looking at the top view of the door. You're looking at the front view. Okay? Here, to simplify the concept and principle of torque, you have to have some kind of a view that will allow you to see the door or the object to have a two-dimensional view. Length and width. Okay? Length and width, or length and thickness. Okay? Okay. So the hinges here. You apply a force. You apply a force. So when you apply a force, you are going to pull the doorknob. So there is that pulling force, F. This is now the F. The pulling force. You open the door. How will you open the door? Well, it depends. There are doors that when you open, you are going to push. And there are doors when you are going to open, you are going to pull. Push or pull is force. Because force is either a push or a pull. When there is a push, there is a force. When there is a pull, there is a force. No push, no force. No pull, no force. Because force is a push or a pull. In the vernacular, okay, ang kusog, usa ka pagtulod o pagbira. Tud, bira. Okay? Duot, 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 ibot. They have the same meaning. Okay? Okay. So you pull the doorknob. Assuming that when you open the door, you are going to pull the doorknob. When you pull the doorknob, the door rotates. The door will rotate. The door will rotate. It will rotate in that way. A counterclockwise rotation. If this is our view, a counterclockwise rotation. Counterclockwise. Because the reverse is clockwise. Okay. Where is R? Our R is the distance from the axis of rotation to the line of action of the force. This is the line of action of the force. This is the line of action of the force. So the angle here is 90 degrees. 90 degrees. Maximum. So you have a maximum torque. If you are going to have your doorknob inclined, okay, the doorknob, instead of this position, the doorknob is here. Here, okay. That's your style. That's your style. Instead of the doorknob having 90 degrees, you want it to be more than 90. Or more than 90. That's your style. So when you pull, it's not easier for you to open the door because imagine you pull the door in an oblique position. Oblique. The best, the doorknob at 90 degrees. We have 90 degrees. Sine of 90. If theta equals 90 degrees, then you have the torque equals RF sine of 90 degrees. The answer here, you will have RF only. RF maximum. Where is the... I'm looking for the cover of this. Oh, the cover fell down. The cover fell down. So, where is it now? Maybe there is a white lady around here. Huh? Oh. No cover. So, I'll just borrow the cover of others. Let me borrow the cover, ha? Let me borrow. So, I ask permission. Because there might be somebody observing me. Even if I am alone here. I have already a cover. Now, so this one. Now, this is the concept of torque. If you are going to move the doorknob, this doorknob, nearer the axis, di ba? From here, I will transfer the doorknob. I will transfer the doorknob here. I'm going to transfer the doorknob there. Nearer the axis, nearer the bisagra, what happens? It will be harder for you to open the door because Because the R here, this R, distance from the axis, this R here, is shorter. When R is small, the product is small. Assuming you will not change the force remains the same. If R, we decrease the R, we shorten the R, we reduce the distance, make the doorknob closer to the hinges, where the hinges serve as the axis of rotation, then R is smaller, therefore the product is smaller. Suppose original is distance is 1 meter. 1 meter, usually our door about that or shorter or a little bit bigger. The door of our house, okay? A little longer than 1 meter, but not 2 meters, Not 2 meters. Oh, 2 meters. This is 1 meter, 1 meter. 1 meter, and you have 2 meters. Oh, unusual, unusual. But if that is your style also, you want 2 meters door, that's your door, that's your house, so be it. Let us just say 1 meter. This is end A, this one is end A, end B, end A, end B, end A, end B, end B, end A, end A, end B. Okay. The doorknob here, hinges here, doorknob here, hinges here. Top view, looking at the top, we see the doorknob, we see the hinges. When you open the door, you pull, you pull, pull. Okay, here. Doorknob, hinges. Doorknob, hinges. Hinges, doorknob. Apply a force. Pull. This end A, end A, end A, end A. End B, end B. Okay? Okay. End A is free to move. End B is a fixed end because it is where the hinges are located. The end is fixed. Okay? End B does not move. Okay? Away or nearer, closer or farther, it remains at the hinges, the end B. But end E is free to move. So this is what we call the axis of rotation. This end will move. This end will move around the axis of rotation. Okay? Okay. So, doorknob here. We transfer here. Apply the same force. It's difficult. You can open, but you need stronger force. The same force, it's harder for you. Why? The torque now is smaller. Why smaller? Because the moment arm from the axis to the force. The force is right at the doorknob. The force applied by you. The person who opens, what do you call that? What do you call that person that opens the door? What do you call the person that opens the door? The one that opens the door, we call him or her the opener. The opener opens. So the opener opens. Doorknob here. You pull. Pack. Difficult. Closer. Difficult. Harder to open. Closer. More harder. At the hands. you cannot open anymore because torque there is zero. Torque is zero. Why zero? I will answer my question. Zero because the moment arm is zero. What is that moment arm? The distance from the axis of rotation to the force applied. And because the doorknob here, you apply the force here, doorknob here, you transfer, because that's the style of your door, you put the doorknob at the hinges, the axis of rotation, you cannot open. Why? The distance, the moment arm from the axis to where the force is applied is zero. If R is zero, if R is zero, zero times the force equals zero. You get that? So, here in our problems, we will be discussing about torques. Okay? So, I will now proceed to problem number 2. Huh? Problem number 2. Okay. Problem number 2. Very heavy. Probably this is 2 kilograms. Probably this is 2 kilograms. The width is wider than my face. The width of this book is wider than my face. The length of this book is taller than my face. And the thickness of this book is thicker than my nose. Okay. So here, I'm going to open now. Example. Wow. Wait, huh? This is chapter 14. Chapter 14 here. Chapter 14. Where are you? Here. Okay. Chapter 14. Chapter 14. The first problem was already explained. Although the writings of the equations there, the solutions, not all were shown because I did not realize the capability of my camera. I'm using my camera. The camera phone, cell phone camera. Okay? I am using here the, well, we have now higher capacity of cell phone now. We already have Samsung S20 Ultra or Samsung Galaxy S20 Plus. My cell phone is not. I am just using A20. So up to this point only there. Okay? Beyond there, you cannot see. What I did, I wrote some here. You were not able to see. So I said a while ago, you just listen to my audio. Because what I wrote, I stated it. I said it while writing. You review that. Okay. Number 2. Number 2 problem. Stand up straight. Number 2 problem. I will read the problem. You are holding a meter stick of mass 0.20 kilograms. So 0.20 kilograms the mass. 0.20 kilograms equals 200 grams. Because 1 kilogram is 1,000 grams. So 0.2 kilogram horizontally in one hand. Okay. Which hand? Left or right hand? It depends on who will be demonstrating that. Assume that your hand is wrapped, so you are the one holding it, around the last 10 centimeters of the meter stick. See the figure. So there's the figure drawing. So the front edge of your hand exerts an upward force, and the rear edge of your hand exerts a downward force. Calculate the forces. Here. So, this is the meter stick. I will use, because I am a leftist, okay? I will use my left hand, because I am a leftist, okay? Holding, this is the front edge of my hand, wrapped against, wrapped, okay, wrapped, 10 centimeters, 10 centimeters, wrapped, wrapped means in the vernacular, gikom-kom. This edge of the hand is exerting a force upward, this one, upward, while this rear edge is exerting a force downward, this one, upward, this one, downward, this edge, upward, the front edge. Okay. Now, but horizontal only, steady, because the meter stick is assumed to be in equilibrium. Okay? In chapter 14, if you have a static problem there, or problem on statics, we always have what we call equilibrium condition. So there, horizontal. So there are two answers, end A and end B. Okay? I am already perspiring. So what will I do? I am inside this classroom where I put off the air conditioner, the air condition machine there, because it will be producing noise to the recording. As you observe in the last video in this chapter, there is sound there, machine, the air conditioner. So I am perspiring, and so I will just continue this one later. We'll take a break. And by the way, at 2 o'clock this afternoon, today is Thursday, we'll have the big blue button. So I'm perspiring already. Okay? I will just continue the discussions. Meanwhile, you know already the concept of torque and the principles involved later. We are going to apply the principles in solving the problems. Okay?